Neuromorphic computing. What is the tech all about? It's a technology that mimics the structure and function of the human brain to create more efficient, adaptive, and intelligent computing systems. Unlike traditional computing, which processes information sequentially using Boolean logic, neuromorphic computing relies on spiking neural networks, SNNs, that process data in parallel, like biological neurons. How does it work? It mimics the biological neural networks of the human brain to process information efficiently. Unlike traditional computers that follow step-by-step, sequential processing, neuromorphic systems operate in a parallel, event-driven manner, much like neurons communicating by electrical impulses. What are the areas where the tech is being utilized? It's inspired by the structure and function of the human brain, is revolutionizing various industries by offering efficient, adaptive, and intelligent computing systems. Unlike traditional computing, which processes information sequentially, neuromorphic systems utilize parallel, event-driven processing, making them ideal for real-time applications that require minimal energy consumption. This technology is being utilized across multiple fields, from artificial intelligence to space exploration, transforming how we interact with machines and data. What impact will it bring? It's a cutting-edge approach to artificial intelligence and computational systems, drawing inspiration from the structure and functioning of the human brain. This technology mimics biological neural networks, leveraging the same principles that enable human cognition, learning, and decision-making. As neuromorphic computing continues to develop, logically, its potential to revolutionize various sectors becomes increasingly apparent. Its impact is poised to reshape fields like energy efficiency, artificial intelligence, robotics, autonomous systems, neuroscience, and human-computer interaction. Basic definition: neuromorphic computing refers to designing computer systems that mimic the architecture and functioning of the human brain. Etymology-based explanation: the term neuromorphic is derived from neuro, nerve our brain, and morphic, shape, short form, meaning brain-like form or function. Brain-inspired architecture: neuromorphic systems emulate neurons and synapses using electronic components such as transistors or memory stores. Event-driven computing: unlike traditional systems that operate in clock cycles, neuromorphic systems are event-driven, processing data only when a signal is received, like how neurons fire. Parallel processing: these systems are massively parallel, allowing for simultaneous processing, similar to the brain's distributed architecture. Neuromorphic chips: specialized hardware like IBM's True North, Intel's Loihi, or Spinnaker that emulate the structure and functioning of biological neurons. Use of memory stores: components that mimic synapses by changing resistance based on the history of voltage, current, suitable for learning and memory storage. Spiking neural networks, SNNs: the primary model used in neuromorphic computing, where information is encoded in spikes, short bursts of electrical activity, mimicking biological neurons. Hebbian learning, a learning rule: cells that fire together wire together, that is often implemented in neuromorphic systems. Simulation platforms: software frameworks such as NEST, Brian 2, or Nengo simulate neuromorphic models on conventional hardware. Low power consumption: neuromorphic systems are energy efficient, ideal for mobile, edge, and IoT devices due to their event-driven nature. Real-time learning: these systems can learn and adapt in real time, similar to how humans learn from experience. Fault tolerance: like the human brain, neuromorphic systems can be resilient to failure in parts of the system. Robotics, real-time sensory processing and decision-making. Edge AI, deploying intelligent systems on devices with limited computing resources. Prosthetics and brain-machine interfaces, BMIs. Neuromorphic chips can interpret neural signals in real time. Cognitive computing, systems that mimic human cognition for pattern recognition, perception, and decision-making. Compared to traditional computing, traditional systems use von Neumann architecture, separate memory and processing units, while neuromorphic systems integrate computation and memory, reducing latency and power. Compared to deep learning systems use dense matrices and gradient descent, while neuromorphic systems use sparse, spike-based communication in local learning rules. Emulating the human brain, neuromorphic computing takes direct inspiration from the structure and dynamics of neurons, synapses, and the overall neural network. Neuroplasticity, simulation, the system's ability to adapt based on experience, akin to how the human brain changes with learning. Coined in the 1980s, the term was introduced by Carver Mead in the 1980s to describe VLSI systems mimicking neurobiological architectures. Computational neuroscience bridge acts as a bridge between understanding the brain and building intelligent machines. Embodied intelligence. Some neuromorphic systems are developed for robots to mimic human-like sensory motor capabilities, suggesting intelligence is tied to physical interaction. Towards AGI, artificial general intelligence, seen by some researchers as a potential path toward building machines that think and learn like humans. Modern computing has made remarkable progress over the last several decades, powering everything from smartphones to spacecraft. But despite this success, traditional computers are reaching limits in terms of energy efficiency, adaptability, and real-time learning, especially when it comes to replicating human-like intelligence. Neuromorphic computing emerges as a promising paradigm, offering an alternative model inspired by the brain. The central question is, why pursue neuromorphic computing at all? This essay explores the multifaceted motivations behind this emerging field. The bottlenecks of traditional computing conventional computers are based on the von Neumann architecture, which separates memory and processing units. This separation causes a von Neumann bottleneck, where data must shuttle back and forth between memory and CPU, consuming time and energy. While acceptable for many tasks, this architecture struggles with real-time sensory processing, e.g., vision, hearing, contextual understanding, pattern recognition with incomplete or noisy data, power efficiency, especially in mobile or embedded systems. The human brain, on the other hand, is massively parallel, fault-tolerant, highly energy efficient, consumes approximately 20 watts, capable of learning in real time from unstructured data. These stark differences inspire engineers and scientists to explore computing that works more like the brain, thus giving rise to neuromorphic computing. The brain is a model of efficiency and intelligence. The biological brain processes vast amounts of data with extraordinary speed and efficiency. A typical human brain contains around 86 billion neurons, connected through more than 100 trillion synapses, all operating in parallel. Unlike conventional systems that process instructions linearly and require large data sets, the brain can recognize a face with a single glance, learn from one example, adapt instantly to changes in environment, interpret subtle cues and incomplete data. Neuromorphic computing aims to replicate not the biological form of the brain, but its function. This includes spiking neural networks, SNNs, that simulate the brain's event-based signaling, plastic synapses that learn through use, Hebbian learning, asynchronous communication, removing reliance on a central clock, power efficiency, the green motivation. One of the strongest motivations for neuromorphic computing is energy efficiency. As AI systems grow larger, like GPT or deep neural networks, so does their energy footprint. Training modern AI models requires thousands of GPUs and massive electricity usage. Neuromorphic chips, in contrast, consume significantly less power, process information only when needed, event-driven, are ideal for always-on devices like sensors, wearables, and IoT systems. In scenarios where power is limited, e.g., Mars rovers, remote sensors, medical implants, neuromorphic systems offer a compelling alternative. Real-time processing for autonomous systems. For autonomous systems like robots, drones, self-driving cars, and prosthetics, decision-making must occur in real time, often under uncertain or noisy conditions. Traditional AI systems may be too slow or too power-hungry for real-time response. Neuromorphic systems, thanks to their parallelism and event-driven architecture, can react quickly to stimuli, filter important signals from noise. learn incrementally from new environments. This makes them especially suitable for edge AI, where latency, speed, and power constraints are critical. Towards brain-machine interfaces and cognitive computing. Neuromorphic computing is not just a computational trend. It is also a tool to better understand the brain. It plays a critical role in neuroscience research, helping simulate and test theories of brain function. Brain-machine interfaces, BMIs, that decode neural signals for controlling external devices, cognitive computing, where systems are built to understand context, emotion, and intent. In medical applications, neuromorphic hardware can help process and respond to brain signals in real time, enabling more responsive prosthetics or adaptive neurostimulation therapies.